Yeah, that's good. What do these guys have in common? What? Yeah, that's good. That's one. They all work here. Yeah. What else?
MIT?
What?
MIT.
Geez, MIT is pretty good. Geez, that's
Okay.
that's good. MIT, Beanstalk, Stein, Seth are 3 out of 5 are MIT. That's right. That's pretty good. That's actually pretty deep. But Goldfarb, Iyengar, Stanford, Goldfarb, Princeton. Yeah, Cornell. I think Princeton, Cornell. I forget. Yeah. The failed stochastics. Yeah, that's right. That's close. The failed stochastics is real close. That's what all these guys do deterministic OR, and they therefore would fail stochastics, right? They would fail stochastics. So somebody's really a step ahead. These 5 allegedly would fail stochastics. They do optimization. These guys are the main optimization people in IEOR. I would fail optimization, right? I'm the other guys. Now, actually, most of the young guys, I mean, there's a tendency. So in our field, you're a Renaissance man, woman, whatever. If in fact you actually know something about optimization and about stochastics, to say nothing of finance and supply chain or whatever, right? But traditionally, people specialize either in stochastics or in optimization, and that's the sort of traditional view of operations research, is that it's stochastics and optimization, and the people go really deep in one of those areas. And so I do stochastics, and these guys do optimization, okay? So what I want to do today is talk about optimization from sort of a really high-level stochastic view. And this is like from Ross. I have some notes that are on. I already put them online, and this is section 4.52 in the book, and then there's notes online. So this is because I have this sort of vague sense that this is going to be totally incoherent. So the thought is that you get a chance to replay this by reading the notes and reading the book. So this is a discussion in the book. So it's in a chapter of the book. It's in our chapter of the book, but it may not seem like it. So anyway, this seemed like. The other thing to remember is the exam Thursday. So that's coming up. And actually, this topic is, you can all sort of go to sleep now, because I'm thinking this topic is not directly going to be on the exam. That was my thought. Yeah?
Do you need no MATLAB for the exam?
No. So that assignment, that MATLAB assignment is not essential for Thursday. You should, for your own sake, you should do stuff with the MATLAB, and it helps you understand, but it's not directly, the MATLAB is not directly. Yeah.
Is that a canonical form, or?
No, you should know that, but I mean, that's not that you need to do MATLAB. So the canonical form in part of that assignment is important, but you don't really need MATLAB to do it. MATLAB just makes it easy. So the MATLAB experience, I'm thinking the MATLAB experience of doing these things, raising matrices to powers, solving some of these things, is really a good way to make you feel comfortable that you really easily could, I mean, if you wrote your own programs, you use the programs, you see that this stuff is really easy to use. Just simple programs will do all the stuff, the computations. So the thing you really could be focusing on is interpretation. It's sort of like if you're, you're doing, I guess today, if you were doing high school calculus, physics or something, and you have the TI-89 calculator, if you're good at that, I mean, you probably, that does all the calculations. So then the questions you might think, not to make your life calculations, you should just understand what's going on and focus on that. So the MATLAB stuff is just but it's very useful. I mean, I wouldn't underestimate, I mean, I'm not emphasizing calculations, but that gives you really a great feeling for what's going on. Yeah?
Is there any way to trace it on Excel?
I don't know. Yeah, I don't know about Excel. I should know, but I think so. I think the answer is, There's add-ons for sure.
I know you could put macros and solve them, but I don't know if you could rate them.
Yeah, I'm not sure.
Like,
Does somebody want to comment to that? Surely somebody here knows the answer to that. I mean, the add-on is one method, because you can get add-on stuff that's stochastic type stuff to Excel. That certainly does the job, but whether you can do it directly, I'm thinking you might have trouble. Yeah.
The problem sets this week, those are to be handed in on Thursday?
Yeah, they can be handed in on Thursday. That's not a big deal. Remember, the homework is not critical. So if at any issue about, make sure you focus on studying. If the homework is turned in then or it's turned in later, doesn't matter. So don't focus on. Certainly don't focus on doing the MATLAB homework at the last minute, because that's not, focus. You right now focus on the exam. Don't focus on busy work. Later on, do the stuff as you have chance to do it. Yeah.
for the exam, are we allowed a calculator in one sheet?
No calculator. No computing aids. No cell phones. No human aids, especially. You're on your own. However, you can bring the Ross textbook, and you can bring a sheet of paper with 8x11 sheet of paper with notes on it.
Homework 4 included?
And all of homeworks 4 is included. So the 4 homeworks up to now are included. The MATLAB is included conceptually, but no computational stuff. So so canonical forms included. Actually, the MATLAB content of that numerical in the non-MATLAB stuff about how to solve those things that you're doing with MATLAB, you should understand. But you don't actually, if you did that assignment, looking at the assignment is good to see what the questions are, because conceptually you should know what to do. Yeah. So, the other thing is it's going to be, I'm planning for this to be in the room downstairs. I'm thinking there's more room there. So next exam is downstairs. Here. Okay. So that's perfectly, maybe it's perfectly reasonable to ask any questions to do with the exam. So the exam is, again, it's 11, usual time, but 11 to 1. So it's 2-hour period. Yeah.
For the exam study, we should focus more on the book or on the assignments, or what should we focus on?
First, for sure, first focus on the homework. All the homework, including the MATLAB, including the numerical assignment, except not from a MATLAB point of view. Nothing about MATLAB. You just forget that you had to do that numerical assignment, but you should focus on all the homework first, homework. Then I would focus second on class stuff, and third on the book. And the book meaning the stuff that relates to the sections assigned. Some of Chapter 3 was not assigned, some of Chapter 4 was not assigned, and I think that was specified. So the homework assignments actually say what sections you're supposed to read. So some of Chapter 3 and a lot of Chapter 3 and a fair amount of Chapter 4 was not assigned. So, but the homework, if you're mostly all right, I think, if you focus on all the homework. But the rest of the thing, there's the class stuff also and the book also. But first homework, and then second the class notes and the book. That's certainly everything. I mean, the book puts you in good shape, so you actually can bring the book with you. So it's a good idea to know what's there and where it is. That's a reasonable attitude. So in a way, you want to think. You don't want to, I mean, it doesn't make sense that you could come to class with the book and learn it in real time if you didn't know it at all, okay? I mean, I don't think that's possible. Maybe you can do it. Maybe some people could do it and just come and start looking in the book. It's good to know how to use the index of a book, for example. If somebody says, well, you ask something about accessibility, communication, one of these concepts, well, you just look it up in the index, right? I mean, surely if there's something that appears, actually you could do quite a bit. Just look it up in the index, find the page, read the definition, and do it. It probably is, I don't know. It would be an interesting test to come in cold with the book and see if you could, okay, there's that level. Actually, a fair number of students should have that kind of ability to do that. But actually, if you've been taking a course and you have the book, that should be able to help you leverage what you know a lot. In other words, if you just know how to look stuff up in the book, if you don't understand some word on there, you can look it up in the book, in the index. So if you know you have the book, you know you have the sheet of paper, the sheet of paper is good to organize some of the stuff that's not in the book, or think about how the book is organized. So in effect, the book and the sheet of paper is an aid, and you should use that.
Is the 2 hours, is that going to be plenty of time for the exam, or will the exam...
I'm a really bad character. I tend to make long exams. I can't resist. I mean, I can't ask a question with just one part. I mean, everything, I got to make 6 parts. So it's kind of long. So I think actually the regular class time of 1 hour and 15 minutes would not be enough. I think 2 hours, maybe the regular class time, if you're really on top of what you're doing, is enough. The full time should be enough. I'm expecting a lot of people to do well, to be able to finish and do everything, but I'm thinking it's going to probably, even those people, it's going to take more than 1 hour and 15 minutes. Yeah.
Are the exams going to be similar in format and like types of questions to last year's?
Yeah, last year's exams, there's the way to, that's intent not to, that's not there to fool you and trick you and make you think, well, now I got him. That's what it was last year, but wait till I nail you this year. Actually, the intent, the idea is it's going to be like the one last year. That's the structure, is that it will be like that. It's the same pattern. So that guide orients you the right way, I think. If you looking at the last exam and its solutions which are posted orients you to what to think. I think that's... And then, that's probably the most important part. Now you can go to sleep, because if these issues were a little bit important, now what I'm going to talk about, this this ode to these fine gentlemen, is sort of not covered. I'm going to say somewhere in this discussion will be a Markov chain. And we'll actually be interested in this Markov chain, but it's not so directly related. And yet it's, I don't know, this is a nice topic. It's sort of a little bit extraneous. The idea is to do something now that doesn't burden you with a heavy learning on this stuff between now and Thursday. So then, of course, there's a recitation as usual today, which is going to do whatever you want related to the homework to prepare for the exam. So he's going to go over the homework at 1. As usual. Okay. Well, okay. Let's see. Well, what we're going to do is we're going to do this thing. Right? We're going to think about linear program. We have a linear program. In matrix notation. So, of course, the matrix notation goes just like with the matrix notation for the Markov chains. And that kind of standard thing we would think about would be, let's take the case of 2 variables. Special case would be, I'm going to just to do a special case here. And I might have, let's go on here. I shouldn't stop. It's important not to stop here. Right. Well, let's see. Maybe I would really actually have let's think of the size. So this is m by n and n by 1. So actually, when I get here, I'm going to be careful here. I might have, actually, when I start here, I would actually want to write this way. So I'm actually, so it doesn't look like this yet. I'm now doing what is the standard thing I think of when I think of a linear program, is I think of a simple problem in 2 dimensions. I'm going to maximize the weighted sum of 2 random variable, two variables, x1 and x2, and then I have these constraints, and they're all less than or equal than the two variables. So I have two variables, and I want to pick x1 and x2 to maximize this, subject to a bunch of these constraints, and the variables are all non-negative. This is sort of in the usual inequality form. This is an equality form. So I'm going from, I'll want to go from there to here. And if I do that, the picture I would draw would be, this is the standard thing you think about. I put the two variables here, and I think, what do I want to do? Well, what are these inequalities? They're things like, this would be x2 less than, this could be this, and then maybe this is x1 less than, and then we might have something like this, right? We have these things where all of these are constraints, so we're inside this region, right, of all these constraints. These linear inequalities, the sum, weighted sum, is saying that we're inside this region here. So we're in this region where the arrows are, and the variables are non-negative. So this is, all these inequalities put us in this region. I'm just now saying this is a typical linear program, but with only two variables, so I can draw a picture. And I've got all these inequalities. Inequalities here, the two non-negativity constraints are this way, and all these other inequalities are lines, and I'm assuming all the A's and the C's are all positive, but different values. So that means all the lines look like this, and I'm required to be in this way if they're all positive. So just for instance, I'm assuming Aij greater than 0, greater than or equal to 0, and Ci greater than or equal to 0. All these are just positive, for instance. So that means whatever they are, I mean, this one, when I make x2, means that one of the A1, the first constant, 0, so I'm just constraining one variable, constraining the other variable, and then linear combinations, and I'm in here. Now the objective, the C1 x1 plus C2 x2, that's on some, it's some line with a slope. This is equal to y. So the values that occurs are some lines. So there's maybe some line here. These lines represent values of the objective function. And that might take me here. So if I'm maximizing this y, which is of this form, I'm picking x1 and x2 on one of these lines to be to get the largest thing I can. And I come to the corner here, the extreme point, that's the furthest out on these lines, where this line is moving out here, and the higher this line is, the more I get. I'm getting this, so I get more y as I go out this way until I can't go any further. And I come to one of these corners. This is, there's a lot more, right? But this is just an idea of the problem. The problem is maximizing a linear function of some variables subject to linear inequalities. Okay, you should all be experts on that. And in 2 dimensions, you can draw this nice picture and you see what's happening. Now then, now you come to the algorithm. So when you do linear program, what you learn is, and then there are big problems, right? So here's this thing we started with just 2 variables, x1 and x2, but you might have thousands of variables and thousands of constraints, and so then you want to do it on a computer somehow. Okay? One of the things you see from this picture, which generalizes nicely, is that you see in this picture that no matter what the C1 and C2, the C1 and C2 just change the slope of this line. And so for any given C1 and C2, you have a line of a certain slope, and then you go out to a corner, an extreme point it's called, the corner. So from this picture you see that no matter what C1 and C2 is, there will always be an optimal solution at one of these corners. Sort of obvious from this picture. And then it's sort of obvious that it also extends to any dimension. That there will be an optimal solution at one of these corners. And then you have to generalize to more variables, more dimensions, but it'll occur at one of these corners. That's sort of one of the fundamental ideas of the simplex method for solving linear programs. Now, initially, even this problem is sort of hard, is the set of feasible solutions is all the points inside this region here. So there's infinitely many x1, x2 pairs that are feasible. Anything inside this shaded region is an okay feasible solution, and I want the best one, and the best one happens to be at this corner. Now, if I restrict attention to the extreme points, I've only got 1, 2, 3, 4, 5. So once I say, oh, I don't need to look at infinitely many in here, it just suffices to look at the extreme points. And that's sort of obvious. Linear function, linear inequalities, it's going to be, the optimal solution is going to be at an extreme point. So that's a kind of an initial observation. So now, for any of these problems, there's only finitely many extreme points. In this case, if I wrote one of these down, yeah, I could write them on the blackboards, all these blackboards, a bunch of equations with 2 variables. I would have all this stuff. You know, if I did 100 constraints and so forth and so on, I'm only going to have, you can imagine doing one of these problems with 2 variables like this, I'm going to have at most 20, 30 of these extreme points. So if you want to solve a linear program like this, you just can look at all the extreme points and evaluate them. Okay, now this is where we begin to come to the business of, well, what does the simplex do? The simplex method starts at some extreme point, say often the one here at the origin. You find some initial point, which in this case, with all these non-negative variables, it's clear that this is a feasible solution down here. And what you do is you move through the space of extreme points. You go from an extreme point to an adjacent extreme point. So you go from, say, from here to here, from here to here, and from here to here. You move around the extreme points, and here you can see that the adjacent, in this picture, the adjacent extreme points are easy to see. There's 2 to each one. If you're here, there are 2 adjacent extreme points, and when you're here, there are these 2. So you go here, here, and from starting in here, in 1, 2, 3 steps, you get the optimal. So the simplex method moves from an initial extreme point to a neighboring or adjacent extreme point so that you improve at every step. And you can show that looking around that if this isn't either this is optimal, this is best, or if it's not best, one of the adjacent ones will be better. So you keep moving, doing better at every step. You start at some and you get to the end. Yeah. Yeah.
You're saying if the neighboring points are worse, then this step can be better?
Yeah. That's part of this is part of the theory. So the theory is you start here and you go to these, you start, say, here, and then you move from adjacent. And if there's no extreme point, if the adjacent extreme points, there aren't many, here there are just 2. Either one of those 2 is better. If not, this is optimal. And if it is better, you move to the better one. There could be ties, not in this picture, but in higher dimensions there could be ties, which is a little complicated. But for simplicity, imagine there are no ties. Then that means this could be the same value and you don't quite know what to do, right? Because you haven't proved anything. But if nothing is any better in any direction, so you have a little bit with ties, a little complicated, degeneracy in ties. But if there weren't any ties, then you're moving along, you're okay.
Is it possible to eliminate a local, for it to decrease, but then increase at a later?
And I guess that's not possible either, right? So then what are these? Let's think about the extreme points. One way to get this problem is, one way to approach the problem, I mean, when you're now starting to do it, you actually convert it into this equality form is a kind of good way to do things. So this is inequalities. You're going to convert it. I want to convert it into this form. So this is actually changing the dimension, because in order to do this, what you do, now I'm just reminding you about linear programming, but what you do to go from the previous thing to this one and make these equalities is you add slack variables. You add extra variables. So instead of 2 variables, there's going to be more variables. Okay, but then you have something like this. Now in here, an extreme point is going to be, you're going to have m positive values and n minus m zeros. Because you're going to have m equations, you're going to have m equations in n unknowns. Where m is less than n. The reason you're going to have more variables is every inequality, for each inequality, you're going to add this slack variable. So if you had m equations to begin with, you might have had m by 2 variables. But you might add m variables, so you're going to, in the end, going to get m by m plus 2, right? If I initially had m equations in 2 variables, inequalities, if I add a variable for each of these m inequalities, I'm going to get m plus 2. So in general, if I use this form, I'm going to have m by n, where there's m equations in n unknowns, where n is bigger than n. But they're equalities now. So I have this form where they're equalities, but these m constraints, these m equalities, this is sort of like if you think of A as part of A as non-singular, you would invert it. But this is bigger dimensions, so there's extra equations. But the thought is, in this context, you really, when you specify a solution of this, well, an extreme point would correspond to picking m positive values and then letting all the other variables be 0. So I'm now kind of going into this context. That's leaving this a little bit, because we're actually making it a little bit, the problem is changing dimension here by making equalities. That's going from starting with inequalities to going to equalities. Now, there's still, so in this case, in this framework, an extreme point is characterized by having n minus m zeros, and the question is m positive values. So you move around these extreme points in the same kind of thing. The simplex method is going to move among the extreme points, and that's going to be, you're going to have, remember, x is now m by 1. So this is the variables you want to find, n by 1, and then candidate x's that are extreme points are going to have m positive values. And to some extent, you get this, you can think of taking this ax equals b. This is m by 1, and this is m by n and n by 1. Imagine taking only m variables, so you take some part of this. A is m by m, x is m by 1, and b is m by 1, and then call this bar. X is equal to a bar inverse b. I mean, imagine taking, this matrix looks like not so many rows, but lots of columns, right? So it looks like this, and this, but you're going to only take, this is n, but you're only going to take a block of m of them, and you're going to take correspondingly m variables. So I'm reducing, this problem's got a lot of extra variables, but remember, we're going to only pick out m to be positive. So if I take a chunk of A that's of size m by m, and I take a chunk of x which is size m, then I could just invert it. And that's how so if I pick some values to be positive, say like these ones are going to be positive, all the rest are going to be 0, then that's an extreme point, and I can just solve for these values. So all I'm doing is reviewing. This is not intended to be anything new. Yeah.
each extreme point corresponds to a given set of picking n.
Yeah, the extreme point corresponds to specifying which of the variables are positive. If you specify these particular one of the n's to be positive, you can find the actual values essentially by inverting, assuming that what's there is invertible. Otherwise, it will be some solution that's consistent, but think of it as invertible if it was what's there. That's the thing to think of. So that an extreme point corresponds to picking which of the n, there's n altogether, and if you specify which are to be positive, that's an extreme point. So, extreme points, how many? How many? How many extreme points? How many are there here? Yeah, n choose m, which is useful to know if you're doing the binomial distribution, right? For example, this comes in the binomial distribution. But that's right? This is how many extreme points they are. In any case, for MEM, NEN, it's finite. In principle, you can enumerate them all. Perhaps you can enumerate them all, right? So given any n and m, where n is bigger than m, this is the number of extreme points. Now, what does linear programming do? Linear programming is an algorithm that will start with one of these extreme points. You find one that gives you a feasible solution, and what do? You move from extreme point to another extreme point, assuming without the degeneracy issue, such that you do better in your objective function at every step. The same idea. You move to an adjacent extreme point where you do better at every step. So you keep moving from extreme point to extreme point until you find the best one. And you're doing this in a way such that you're sitting at some extreme point. So when you change, now I'm kind of getting into the pivot of the simplex thing, you're going to move to an adjacent extreme point. That's going to mean taking one of these positive values out and putting some other value positive. That's exactly how you go to an adjacent one. An adjacent one is one for which these m positive values, one of them is made 0 and something else is made positive, just one. You switch one positive variable and one 0 variable. You switch their role. That's the essence of the pivoting step. The pivoting step tells you exactly what the values coming in and out have to be. But you essentially make, maybe you make this one positive and you make this one out, right? You switch. This that was positive becomes 0 and this becomes positive. And that's making it an adjacent extreme point. And you keep doing this until you've gotten it can't improve, and you're done. And if it's big, you use Cplex, or you use Karmakar's algorithm or something else, right? These guys tell you how to do this. Now, we haven't even got to the probability, but there is a probability. There's an issue here. So I think the question that's natural to ask, and maybe I would think you don't ask when you do optimization, is why bother? I mean, there's the level that I wouldn't ask is, why should you solve the problem at all? But let's suppose you do want to solve the problem. Do you really need this linear programming? I mean, linear programming is going to tell you, be an algorithm to move to these adjacent extreme points. Okay, now what would be sort of a reasonable attitude to take until proven otherwise is say, hey, this stuff might have been good when Goldfarb and I were in school, 100 years ago. I mean, we were doing the stuff on abacus, right? And now we have computers, and we have Moore's law, and the computers are getting faster like mad, doubling in speed every 1.5 years. Surely, all we have to do, like that problem, there's one we just looked at, had 5 extreme points. Let's just write a program to enumerate all the extreme points, evaluate them, and find the best one. What do you need linear programming for? Just go through them, enumerate them all. I mean, you ought to be, right, why learn something if you don't need it? You ought to be convinced my point is you ought to be convinced that the linear programming is doing something for you. I mean, why not just enumerate them all, right? You could easily write a program that will go through these systematically extreme points and put m variables here and change them. Go through them all. That's not hard to do, to write an algorithm that would go through, successively list all the extreme points, and it's easy to evaluate them. You can list the extreme point, enumerate the extreme points, evaluate, see if it's feasible, see what's the objective function, pick the max. Right? That's the reason why this stuff, these guys are, might be raised is that actually is, that obvious procedure is actually not feasible in some cases. Okay, if the problem's big, and now you want to be persuaded that if the problem is big, it's not feasible. That's the point I want to make. So the idea is, think of a big problem. So my idea of a big problem is n equals 8,000 variables and 1,000 constraints. I mean, maybe we're doing the diet problem in gory detail. So we've got to, the diet problem is like you're going to maximize your health somehow in terms of some linear function of all these things. You've got to have so many vitamins of different kinds. But anyway, you have a big linear program like this, and you want to see that what you want to see is that if you simply enumerated these, it would rather be hard. And if you do the linear program, it should be easy. Now the point is not to do the, you see, a different issue is do the linear program, do the algorithm. I don't propose to discuss doing the algorithm. I just want to think about the algorithm. So the idea is, let's just make a probability model of the algorithm and see how long the algorithm, estimate how long the algorithm would take, and compare that to how long it would be if we enumerated them. We would like to see that if we enumerate the stuff, it's way too hard. And if we do the algorithm, it's going to be easy. So we make a case that the algorithm's worth it. Then you can go learn it. Okay, so this is the thought. So, well, the first thought is, how big is this? So if we let n equals this, equals this, equals the obvious thing here, there's our problem instance. So there are this many. It's a finite number. There's this many extreme points. And the question is, given that, how many extreme points are there? How big is that, roughly? And then how long should the linear programming take, approximately? Okay? Now, the first thing, it's probably the least obvious of all, is that this is a really big number. This is an amazingly big number. And then the notes kind of go through I was looking at my notes, I was trying to make sense of them, I was having trouble. There was a moment, this was one of those cases where I was reviewing when I did this thing before, and I'm reading these, you'll read these notes, they're there. I'm reading the notes, and gee, this is weird. I'm trying to reboot on these notes, and I'm thinking, well, I started in there with something about, there's some web page I found about how many atoms there are in the universe. I mean, this sounds like Hellfand in Frontiers of Science stuff, right? Comes out, so the atoms in the universe, there's an estimate in there, somebody's estimate, that this is atoms in the universe. That's this. There's some business about Avogadro's number. This is the number of atoms in a gram mole substance. Okay, this is actually like we're getting into real engineering sort of. This is like you're the civil engineer building the bridge. This is the OR analog of that. right? We're thinking about this. Okay, so this is the number of atoms in a gram mole substance. So then you might think of how many, there's some calculation about how many atoms are in our galaxy and how many galaxies are there in the universe. I mean, I'm losing grip on this thing. Somehow it sounded good to me at the time. That came out to this. Then there was, the other part here was to think about what we're going to do, our computational speed. So anyway, this is intended to be, this must be big. Just in case you were in doubt, the idea is that must be big. 10 to the 81 must be big. Then let's see, how would we, if we were to enumerate them, how fast can we do it? So my thought was we do 1 trillion calculations per second for a century. Is a rough estimate. So, I did this. So a trillion, right? 10 to the 12th. There's a trillion. And then seconds per year. Trillion seconds per year. Well, years per century is not bad. That's easier. Years per century. This one I can do. I can handle that one. But then, you get, this is trillion calculations per second. This is how many, if you do 1 trillion calculations per second and you do it for a century constantly, this is how many calculations you can perform, 1 trillion calculations per second over a century. So something that's less than this, but this is about how fast you're going to do it. Now, maybe the computer power goes up by several powers, so let's say maybe 10 to the 25. How many calculations you're going to be able to do, whatever, right? Moore's law is operating at powers of 2 every year and a half or something, right? It's going to have a hard time changing that too much. It's going to be a while. It's going to be a while. Now then, okay, so the issue then, this is a frame of reference. So the issue is, how big is this? And secondly, how big would the LP, how long would the LP be in a simple model? You're knowing that the LPs work. You know that this is not a big LP. You know from your courses, surely you can just solve that with CPLEX. 8,000 and 1,000 is actually not big. So you know that you can solve this, but it's challenging. Maybe you can't do it too easily with routine package, but it's solvable. But so therefore it must be manageable. So there must be some story. Okay, well, so we first want to see how big would be this enumeration, which is really really neat that you think about this. Here's these Avogadro's number of atoms in the universe, trillion, how many trillion calculations per second for a century here. So now we want to think about this thing. So we start with this issue, how big is n factorial? So actually this is a good thing to know. It would be good to have this in your mind about how big is n factorial. This is, that's sort of the thinking that's going on here. And does somebody have, there's a simple answer, well, there's a complex answer to this. There's a complex answer to, so what is the complex answer to this? Roughly, how big this is. What name am I looking for? A name that answers this question. Not Goldfarb. Sterling. It's actually in the book, Formula 4.3. This is Formula 4.3 in the book. And I won't remember it all. I won't remember it. What is the sucker? What did I forget? Dang, I guess I didn't forget a thing. Okay, this little squiggle means if I say Fn is squiggle Gn, that means that Fn over Gn goes to 1 as n is going to infinity. So for big N, this thing tends to be like this. Now that's a mess. Actually, the reason why I forget it is you don't want to remember that. You want to remember this would be better. That I can remember, right? This is about what I can remember. And why is this the thing? Well, I've got n to the n here, and I've got e to the minus n. I'm ignoring square root of n. I'm ignoring square root of 2 pi. I mean, if n is 8,000, what do I care about square root of 2 pi? I'm thinking of power orders of magnitude, and even something even larger, right? So this. And I mean, this thing is, a way to think about it is, well, this is n times n minus 1, blah, blah, blah. So this thing has got to be less than n to the n, right? Because this is the product of n numbers, all of whom are less than or equal to n. But then it's something, it's sort of the order, I mean, a lot of them are big, like n. So, I mean, this makes sense, right? This is this is something like n over 2.7, right? That's this thing. So we have that. Okay, so then you do all that. So you do that here. You say, okay, let's take, this is 8,000, so let's carry this out. So what does that mean here? If we do this, well, so you might do it this way, where now we have m equals 1,000 and c equals 8. This is sort of to simplify the problem. I have a big M, and then I have a multiplier here. So this is 1,000, and c is 8 times 1,000, right? So I do that. And then I have Cm factorial over Cm minus m factorial, m factorial. Okay. Now I'm doing this calculation, so I'm thinking this is Cm over e to the Cm, and Cm minus m over e to the Cm minus m, and m over e to the m. That's approximately. So I'm just plugging that in, doing this stuff. Okay, so let me just sort of let me go to where I'm going to, which is something like this. It's let's see if I'm getting this right. Okay, so what I've done, I've just gone through this thing and this, and if I do this, I get 10 raised to this m, collecting all these terms. I get 10 raised to the m log base 10 e times c minus 1. So this looks like 10. Now in our case, 1,000, and then log base 10, 2.7 times 7. So to base 10, this thing turns out to be this. Okay, I'm not going to, if in real time, I'd probably spend another half hour trying to do the arithmetic. So it's in the notes, but you do this stuff and you apply the asymptotics, and you see that the number of extreme points in this case here, this, just to emphasize again, this is approximately 10 to the 1279. Okay, so you do that, it's a little strange. It's worth contemplating. It's worth contemplating that you make up this simple thing, this math function. Here, this is very well defined, finitely written down. No problem. 8,000, choose 1,000. And yet the number of this number, which looks harmless, is actually this, which is monstrously larger than the number of atoms in the universe, evidently, which is an oddness. It's an oddness to contemplate. So if you wanted to somehow list them, you could maybe match them, use a single atom to keep track of each one. You would nowhere near be able to match them to all the, right? You're getting nowhere close. Anyway, this is sort of, this is monstrously bigger than the number of atoms in the universe, that calculation. It's monstrously bigger than what you're going to compute doing 1 trillion calculations per second for a century. I mean, really monstrously bigger, right? I mean, and that's allowing for computer power to increase. So if we do get where we can enumerate it, it will be something fantastic will happen. I mean, right, there'll be really something fantastic. So one point of the linear program is to realize that this thing, if you were to enumerate it, it's clearly totally impossible. Totally impossible. It's very important to understand that the problem really is worth a special technique, because you just can't. The computer is not going to solve it for you. It's not going to happen. You're not going to enumerate it. That's some of the engineering things you're going to have to estimate stuff and say, what is this possible? Okay, this is to say, simple enumeration just isn't there. I mean, you could make anything else. There's a lot of other things that are impossible that you could think of doing, and this would be no easier. Okay, now, here's where we make the Markov chain. We say, but what about linear programming? Let's make a simple model of linear programming and convince ourselves that linear programming ought to be able to do better. Now, that's not getting into the details. I mean, the proof is there. You do it and it works, okay? But just think about how long the linear programming should take. So here's the simple model of the linear program. The simple model is, we're going to go from extreme point to extreme point. Good thought. All along here we're thinking of just enumerating the extreme points. But now we're going to move from extreme point to extreme point in such a way that we're always going to improve. So how long should it take? So a simple model is, suppose we start at some extreme point and we move to another extreme point, but it's going to be one of the others that's better. So we're at some time, we're at the jth best, and we move to one of the j minus 1 bests with probability 1 over j minus 1. In other words, if you're at the jth best, you've already arrived at there's only j minus 1 better. The next step will take you to one of the better ones, because you're always improving, but it'll be, let's just assume it's equally likely to be any of the better ones. And then you move there, and then from there you do the same thing, you repeat. So you start somewhere. Maybe for simplicity, you start at the worst extreme point, which would have been the case like when we started at the origin in that picture. If we start at the worst extreme point, we're then saying, well, there's n of them. So initially, we pick with, you pick the worst one, you'll go to one of the n minus 1 of the other ones, right, in the first step. In the first step, you start at the worst, and you pick one of the other ones, the n minus 1 other ones, with equal probability. You're now at jth best, where j is uniformly distributed on the integers between 1 and n minus 1. And from there, you go to repeat. You keep repeating. So you could have Markov chain would be xn is the rank of the extreme point at nth step. x0, let's see, suppose we make, this is best, rank, so x0 is n, the nth best, the worst. And then xn is the rank, and so in the x1 is the probability that x1 equals k equals 1 over n minus 1 for 1 less than k less than n minus 1, right? Because at the first step, we'll be at the kth best extreme point with probability 1 over n minus 1 for each k from 1 to n minus 1, because we'll pick one of the better ones with equal probability. So we're not trying to model linear programming exactly. We're trying to capture the spirit that it moves from extreme point to extreme point and does better at each step. So we assume at each step we just are going to get one of the other ones equally likely, just to get an idea of how long this ought to take. And I contend that this sort of captures the spirit of what's happening when you do linear programming. Now, you can ask and think about, well, in linear programming you have to move from adjacent extreme point to adjacent ones. Now, you have n extreme points, but there are m of these basic variables. So how far away are you from the optimal extreme point if you start at the worst? If you start at the worst, at most you have to take your m initial variables and change them all, right? So you could change these in m steps. In other words, these could all be wrong. And when you move adjacents, you put one new one in and take one out. So linear programming has to be greater than or equal to m in some sense, m steps. Because if you started at the worst and you moved to adjacent, you'd go in order of m steps. That's sort of like if you just proceeded in a good way. You would actually replace variable by the ones you needed, and you'd make in m steps, you'd move to adjacent extreme point to adjacent. So this is the adjacency. Just the issue of going to adjacent things forces you to have to do, in general, m steps. But m is not too bad. That's saying if you always improved in that sense, in other words, what happens here is you always replace a bad variable with a good variable. That does not happen when you do linear programming. I mean, this is assuming that you start with m bad variables and you go to m good variables and you always put a good variable in instead of a bad one. Not that you're extreme points, but if you always improved, always put the right variables in, you would in fact do this in m steps. So you can't, that would be 1,000. So here, that would be 1,000. So we really can't expect to do better than 1,000, but 1,000 would be okay. So if that's all the issue was, we'd be in no trouble, because if we just could improve when we do that each step, this would be 1,000, and 1,000 is not this. 1,000's fine. I'm just saying this is a simple analysis that says there's no way you can do better than 1,000, because you could just go adjacent and improve one at a time, and there's m steps to do that. But in reality, when you move from adjacents, you don't improve the variables all the time. So that's this. We anticipate that this thing is going to be, the number of steps here is going to be bigger than m. The issue is, how is it close to this? Right? So when you move around these extreme points, it should be at least m. The question is it close to this? Okay, now here's where Ross is very clever. He's full of it. He's got mixed up these really tricky problems and these great examples. This example is also great. This has got a way to look at this problem, which is admittedly unreasonable that you should think of such a thing, that when we work on these problems, sometimes the problems are such tricks that you would never reasonably think of this trick. This is like that, I think. But anyway, as you do enough of these, you learn these tricks. So one way to approach this is to say, let Ti be the number of steps in the LP, starting in ith best. And then if you would see that the probability, you'd see that Ti would be 1 plus, and then 1 over I minus, so the expected Ti is 1 plus 1 over sum j equals 1 to I minus 1. ETJ. Now this is sort of the idea. This is one idea that's straightforward. The expected number of steps you could solve recursively. You'd say, well, starting in I, the expected number of steps is 1, when I take that step, plus with equal probability I go to one of these steps that's jth best, where j is ranging from this, and this is the number of steps remaining. So I could recursively solve this, so I would have solved for this recursively with this. Now from this, you can show by induction this. That isn't the clever part. You can do this by induction. I mean, that's not that hard, but it's actually tedious. It's in the notes. I wrote the thing down. I don't know, it spent me about a half hour over breakfast trying to remember how to do this sucker. This bothered me no end. But it's actually not that hard, but it's confusing. But it's in the notes. You can do by induction, you see that this thing actually has this simple solution. Okay. So then that's actually the key to the answer. But I want to say another way of looking at it. So what Ross does is he defines another way of looking at this that's much more informative, is he defines another stochastic process. The stochastic process I first said, well, on the first step, which extreme point am I at? And then each step, it's successive, what rank am I at? His point is he defines a variable ij where this is equal to either 1 or 0, and it's equal to 1 if the jth best is ever visited. So he just doesn't consider that natural sequence of what you do through successive trials. He just defines these variables. There will be n of them, capital N of them, which is whether or not you ever actually hit the point, the extreme point that's jth best. Do you hit it or not? This is the kind of why would you look at that? Now the odd thing is, this is not only a Markov chain, these things are independent. Totally unobvious, but easy to check. It's easier to prove this from this as well. So you say, well, I'm going to look at the probability that ij equals k, given that ij plus 1, given j plus 2. Well, it's going to be a Markov process at any rate. They're going to be a Markov process. I want this to go all the way to n. It's going to be a Markov process. So I'm going to be given, well, let's see what it is. I'm going to want a Markov, I'm going to want to look at this condition on all the, I'm going to be looking at all of these. So I'm going down this way. And I'm going to look at, I'm not writing this right, ij plus 2. I'm going to be going it's going to be a Markov chain because I'm going to be going this way. I'm going to be conditioning on this history, and I'm going to look at the probability that this could be 1, say, because that's what, it's going to be, what's the probability I visit the jth one, given that I have done whatever I've done here, whether these are 0s or 1s. So I'm conditioning on whether I visited these. And I want to see what this is. This is j plus, this is the one's bigger, the bigger one. So it's going to be conditional in that direction. So I'm going to want it to be a Markov chain going down. So I'm conditioning on all this, and what do I get? So the thought is, well, let's consider what I'm conditioning on. One of these, let's say n, in equals 1, and then ik equals 0 for j plus 1 less than or equal to k less than n. So this n is the smallest one of these that's a 1. The last one before j that I've actually visited is n. And then I ask, what's this? So I know there's a 0, 0, 0, and then there's a 1 at the nth place. because I haven't specified, these are given, so I know what they are. Just take this case. And I look at, okay, the last one visited is n. So then I ask, what's this? Well, if I know that it's n, if it was at n, I'm thinking, well, what am I going to visit? I'm going to visit each thing from here. The next one is going to be j, starting with here, with probability 1 over n minus 1. Because if I'm sitting at n and I'm at the nth bus, what am I going to do next? Well, that's this and this, and the next one's going to be j with this probability. On the other hand, if I'm sitting at n and I don't visit these, I'm saying what's the probability that this happens? And that's to say that I'm in one of these here. So there's down there are j over n minus 1. In other words, the event that I'm talking about, going from the nth best to the jth best, is picking 1 out of n minus 1. But going from here to none of these and down here, or anywhere down here, there's j down here. So the fact that these are 0 means the next one's one of these j. So that's this conditioning event, which is this. Did I pick this right? 1 over j. J. If I'm sitting at j plus 1, okay. So what you're getting by doing this is the probability that the jth is visited is 1 over j, independent of where this n was. You just calculate and the n drops out. So this is a trick to look at these variables. It's a little confusing, but you'll see this is written in Ross. It's written in the notes. All you do is look at these variables, which are just recording whether or not the jth best was ever hit in this random procedure. And if you look at these, you'll see going down that you have this independent of that. So each one is independent of the past. So they're all independent. That means you're going to get this. You're going to get this formula here where, now I should have this should be 1 over j. Did I do something? I'm thinking I might have, should be j minus 1 because my index might be off 1. Okay, well let's leave that point here. This is an odd way to look at it. So there is a way of looking at this that gets these to be independent, and you're getting a formula like this. So when you do that, this is actually a very classical thing in mathematics, what this is, sum of these reciprocals. So when you do engineering problems, it would be easy to arrive at this, and you might remember that you would estimate this by doing something like this. There's more in the notes, but if you're thinking, so you're thinking of this. And you can bound this above and below in this way, right? This sum can somehow be related to this, where you're looking at, you're doing approximations, and you could be looking at it this way, or you could be putting it here. So you're relating the sum to the integral. So if you want to know what this is. And so this thing is going to be log k. Right? This is log k minus log 1. This thing is exactly log k. And this is approximately log k. So this is sort of standard when you see this, that you should know that this thing is approximately log I. So that means back here, that LP is approximately log n. Log n rather than n, right? So that when you went from enumerating the extreme points, you were at, enumeration was 10 to the 1279. Now you're, this is log base en, which changes things a little bit. But this thing, if you go to that thing, you're getting something like 3,000. Okay? So you see that, you'll see if you just do this kind of calculation, which is a little bit extensive to say back of the envelope, but if you analyze the thing, you would estimate by this argument that LP ought to take around 3,000 steps to do this, where a numeration would take this. And so this is totally impossible, and this is feasible. And that you could think, and that when you get these computational algorithms that produce order log n or something, that's fantastic. It's really buying you something for these big problems. So this is really, now the odd part here that's a little bit probably not believable, I would say not believable, is that these random variables, these ij's, were independent and they're Bernoulli. So by this algorithm, this model, you can actually calculate the variance and the distribution of the thing. And it tells you that the variance is also log n. And the standard deviation is then very small relative to the mean. So it would tell you, it's going to tell you that your 3,000 plus or minus something, something like this, which is very unbelievable, right? I mean, you could try, this part is beginning to do, the model isn't like this. Real linear programs aren't random like that. I mean, this is telling you that the actual, if it's a big problem, it's going to take you almost precisely 3,000. I mean, so one could investigate such things. It's probably the model is no longer believable at that level. But roughly speaking, this is about right. This is about right. This is probably very doubtful. But in this case, since the random variables are independent and the means are like this, you actually could say, well, it's the time should be approximately normal with this mean and this variance, and that's probably not correct. But the model, by doing the Markov chain model of saying, let's model this thing roughly as a Markov chain, you could see that indeed you should take about log n instead of n. And log n is about 3,000, whereas n is off the charts. Yeah, so if this has given you a headache, you will indeed now, if not before. If before it wasn't obvious, but now you're glad that this is not on the exam, right? You're glad now that this is not on the exam. Maybe not. You weren't sure before, but now you're glad. So there's a recitation to discuss the homework and whatever you want at 1, and the day of reckoning is Thursday downstairs. Yeah, I guess so. Yeah. Yeah, it's at I think it's 11 o'clock. I'll try to be there.